So we'll go to module 2 chapter 6, which is on reinforcement learning. Now, unlike supervised, unsupervised, and these kinds of learnings where you classify a data entity or where you try to cluster data entities, reinforcement learning is very different. Slightly a more complex subject, but generally speaking, and reinforcement learning was not that popular till the advent of some of these new models like ChatGPT and other generative AI, because there also we use a lot of reinforcement learning using human feedback, etc., etc. So we don't have to become too much of an expert on reinforcement learning, but we need to understand theoretically and on a high level what reinforcement learning means and how models that use reinforcement learning, what kind of risks they can get introduced, and how can we mitigate them. So what happens in reinforcement learning is, you can think this as more of a trial and error method. So you try to do an activity. Okay, now when you try to do an activity, in any activity there are steps. Okay, so you do step 1, then you do step 2, and then you do step 3, so on and so forth till you reach the step which is the end step. Okay, so this is how you do an activity. So let's assume that you are trying to make tea. Okay, so if your activity is trying to make tea, you will take some water, boil it, and then add sugar, add some tea, milk, whatever you want to, however you want to prepare it. Now at each step there can be multiple options. So when you are in step 1, you can either go to step 2, or let's suppose you can go to step 2 dash, or you can go to step 2 dash dash. Okay, so now if you want to make tea, do you want to wait till it goes to 100 degrees Celsius and then add sugar, or you just want to maybe use some sugar free kind of stuff and don't want to add cane sugar, or you may want to do something else. So there will be options at every point of time, and then this can expand like your tree, and at every step there is going to be more options. So I'm just trying to tell you the scenarios in which your reinforcement learning can actually play an important role. So if I have to represent this step-by-step activity chart, I can say that I am in a state S, which can be your initial state, and then I move on to another state which is state 1, and then I move on to another state which is state 2, and eventually I move to my end state. Okay, this is how it is. Now there is someone who is trying to make the decisions. Okay, this person or this entity is called as actor. So there is an actor involved. In case of in case of making tea, it is you who is the actor. In some literature you may also refer this as an agent. So agent or an actor means the same thing. Then these are the things that you need to do from when you have to go from one state to the other state. This is called your action. Okay, so an agent or an actor is going to take an action which is going to move this from one state. So this is a state, all of these are state, this is also a state. So these are some of the terms that you need to understand when you study reinforcement learning. So an agent takes an action which takes him from one state to the other state. So state is your being in a particular environment or in a set of conditions. Okay, and then what happens, I'll tell you one or two more terms that you should know, which are slightly more complex or more difficult to comprehend, so there is a term called as reward. Okay, so now what happens in every activity that you do, there is a goal that we are trying to pursue. In case of making tea, you are trying to reach a goal of making a good tea. Okay, so if the goal is to make the good tea, then then you need to find out that if you go from state this S to S1, how close you are going to become to this goal. Okay, so if you're in making tea, if your goodness of tea can range from 0 to 1, then we need to understand that if I take this action, I can come more close to 1. Eventually, by the time you are here, you have to come as close to 1 as possible, make as good tea as possible. So the reward means that in each action, what is the incremental award that you are getting to reach to your goal state. Okay, so there is an immediate reward that you get here, and then there is an estimated award that you can estimate, or we can say that, okay, you are in state S, okay, and then you take an action, you go to state S dash, and then you are coming from some state and you have to eventually go to some state. So now the reward that you have actually accumulated, that is reward, your actual reward. And then there is an estimated reward. Let's suppose this is your final state, this is your estimated final reward. Okay, so the reward is broken down into two parts. One is what you have accumulated till now, and one is the expectation of the future award. And so at the end of the day, when you are doing this reinforcement learning, what are you trying to find out is, you are trying to find out what is the best possible set of actions you can take at a state to reach your goal. Okay, so this is something that you are trying to find, the best possible actions that you can take at each state, so that you reach your goal more closely, more accurately, more optimizely. And this particular thing is called policy, and this is generally represented by pi. Okay, so these are some of the terms that you should know: state, action, goal, actor or an agent, reward, which can be your accumulated reward or your estimated final reward, and the policy pi. Now while you are doing this particular activity, or whatever you want to call it, you operate in an environment. Okay, so if you are making tea, you are operating in an environment like your kitchen, which is more like a static environment. So whenever you change from one state to the other, your environment will not change. But if we take an example of, say, you being in traffic and you need to go from point A to point B, and there are a lot of intersections where you need to make the right judgments, then sometimes that environment can be a dynamic, not static, because there are other cars that are moving in, moving out. So your decision at any state can change based on how other actors or how other entities who participate in the same environment can be. So that's how the word environment is, that it is it describes in the periphery of your working conditions. Okay, so now you can say that that let's suppose if this is an agent and it is at some state, it needs to take some action based on a policy, and this everything resides in some environment. Okay, so this agent is going to take an action using a policy by and it is going to, at every state it is going to go back and see what is the policy to be used. So this is how reinforcement learning is, or this is how reinforcement learning is generally discussed. And then there is a problem which is called as MAB. Okay, it's called multi-arm bandit problem. Okay, so there is a problem, very famous problem, which is called as MAB, or multi-arm bandit. So what this means is that there is a customer, okay, or there is a person who likes to play, he likes to bet his money in some kind of a casino, and then there are multiple slot machines. Okay, there are multiple slot machines that are there. And these slot machines, they are very, they are like, it's a luck based game. So he doesn't know which slot machine is good and which slot machine is not good. And he goes with some money. Okay. And he needs to spend that money on one of these many machines. Let's suppose in this case, we are talking about 4 machines. So he needs to select one of these machines. And then based on, we need to find a policy where he can maximize his profits. So now there can be 2 things that he can do. Either he can select this randomly, or he can do some kind of a math or do some kind of probability and some kind of pattern matching, and make the selection mathematically. Okay, so these 2 terms in reinforcement learning, in context of reinforcement learning, is called as exploration and exploitation. So exploration, as it means that he wants to explore any of these options. Okay, so he wants to explore any of these options. And exploitation means that he wants to exploit the data that he already has based on the history of events, or based on his skills, based on skills which he would want to use. So let's suppose this is kind of an iterative game. So at t equal to 0, he doesn't know anything. So he goes to, let's suppose, so this is slot machine 1, this is slot machine 2, this is slot machine 3, and this is slot machine 4. So he goes here and he loses his money. Okay, so whatever money he has, let's suppose he has 10 rupees and he puts 1 rupee here and he loses. Okay, now at t equal to 1, he knows that at slot machine number 2, the probability of loss is 1/1, and he doesn't have anything, apart from others. So at t equal to 1, he goes to slot number 3. Let's suppose he wins it, and then at t equal to 2, he can again go here because he knows that this machine is going to give him a win, this is going to give him a loss, but he loses it. And then at 3, he can go here and probably win or lose, etc., etc. So he is going to do this iteratively over a period of time. He is going to get more and more information of what is the probability of winning in any of these 4 machines. Okay, so let's suppose he says that, a slot machine number 1 gives him 70% winning probability, 2 gives him, let's say, 50%, 3 gives him, say, 30%, and this one also gives him, let's suppose, 75%. Okay, now he will have this information, and as he plays more and more and more and more, these numbers will become more and more refined and more better. Okay, they will not do much fluctuation. So if he wants to use this information for making the choice, entirely this information for making the choice, that will be called as exploitation method. And if he wants to do a random guess, it's called as exploration. So in real world, what we want to do a mix of both. So that's called so if you want to mix both these things together, it's called as a epsilon greedy approach. Now in this approach, what we do, we take a value of epsilon between 0 and 1. Let's suppose we take the value of epsilon at 0.05. Now we generate a random number. Okay, so 0.05 will come here between 0 and 1, right? A lesson on the left side and more on the right side. So if I generate a random number and it falls in this range, then I exploit, and if it falls in this range, I explore. So this is how most of your real world algorithms will pass, because if you always keep exploiting and you never explore, you will never inculcate new information. That's something that we keep telling also, that let's suppose you like some particular type of food, you like Indian food, you like some other food, and but unless and until you don't explore other options, you will not even realize if there are better things in this world which you may have missed. Okay, so that's how this exploitation and exploration comes together in the real world. And then there are some mathematical formulas in your reading, which is the intuition or math intuition of whatever we just spoke. So one of the formula says that it says that the probability of choosing a state is sigma 1 upon n and r of j. So these kinds of formulas are there. Q of n k equals to this, or Q of n and k is equal to 1 upon n, which is simple. What I was also telling you above, that how do we get these numbers? These numbers are nothing but the cumulative sum of all your probabilities, all your win or loss, divided by the number of counts that are there. Okay, one more thing which I would want to tell you is that there are two matrices that you should know when it comes to reinforcement learning. One is called a value function, and the other one is called an action value. Okay, now value function is generally denoted by V, and this tells me how good a state is. So this is going to give me a empirical or a numerical indication of the goodness of the state. Okay, and the action value function, which is going to be generally denoted by a letter Q, is going to be the goodness of an action in state S. Okay, so this tells me that if I'm in state S and I have multiple actions to choose, what is the action value, what is the goodness of the action that I'm going to take. So this is something that I don't want to confuse you, but just I want to tell you how important this is, that if you see how DeepSeek has created an LLM in the recent past, so they have changed this action value function for kind of tweaking their their implementation of um, reinforcement learning to make sure that the learning becomes better. Okay, so there is something called as a group policy that they have used, where they try to find out in a state S what are all the actions that they can take. They can find the mean of all those values, and then we find how a particular action, how far it is from the mean value, on the positive side or on the negative side, and then try to normalize it, and then eventually they take the final action. Okay, so this is so important that the greatest and the biggest models of today are also using these matrices to build their models. So this is the basic if you are able to understand this so much, I think this is good enough. You don't have to get into too much of details. This is just an overview of reinforcement learning. So let's get into the other reading, which is also a part of reinforcement learning, but it is called as Markov decision processes. So Markov decision process is a simple process. What this means is that if you are in a state and black, okay, so if you are in a state, say S of t, or let's say, it doesn't really matter whether you have come from this state or that state or anywhere else. So all your historical states does not matter. Okay, it only depends, so my being in state t, and then I go to, let's suppose, state t plus 1, then any action or the value which we said the goodness of a state st plus 1, or the action that I take in state t plus 1 only depends upon my previous state st and not anything else. That's the Markov decision process. There is a complex math behind it, but we don't want to get into those kinds of details. And mathematically you will see these equations like this, st plus 1 is equal to small s t plus 1, assuming s of t equals to s of t. So you'll see equation like this, which is exactly what I was referring to in this diagram, that the probability of being in state t plus 1, which is a state s of t plus 1, is dependent only on what it was at state at time t. Okay, so we don't care what it was at t minus 1. So eventually st will depend upon st minus 1, st minus 1 will depend upon st minus 2. But when you are in a state, you only take care about, or you only think about what was the state previous to this. Okay, you don't keep too much of history. So that's the Markov decision process on a high level. I don't want to get into more details here to avoid confusion. Then there is a mention on what kind of approaches we can take in case of reinforcement learning. So basically there are two kinds of approaches that we should do. The first approach is called the value-based approach, where you find the we can create a matrix like this, where you can put states here, and then you can put states here as n1, s2, etc, etc, and then you find out the transition value. So if you are in state s1 and you want to go to state s2, what is the value function here? Okay, so this it's like maximizing the reward of being in a state and movement into another state from that particular state. So these are called value-based approaches. And if you most of your reinforcement learning algorithms, like your Q learning, your temporal difference, etc, or deep Q learning, are like this. The second approach is called as your policy based approach. Okay, and this policy based approach, it finds the optimal policy to map a state into an action. Okay, so most of our future conversations in this chapter is going to be more on your algorithms now, and then we'll give we'll close this chapter. There is, if you want to read more, you can read more. If you have doubts, you can post me the doubts and I'll hear, but don't over engineer your effort and thoughts only on reinforcement learning, since this is quite a complicated subject. So there are two algorithms that Garp talks about. One is called the Monte Carlo method. So Monte Carlo method, what this does is that, you know, they conduct trials, repeated trials. They conduct repeated trials, and then they, you know, for, let's suppose that, you know, you have this policy pi, which can be multiple policies, you know. So for each policy they will conduct multiple trials so that they can find out the value of, you know, the action value pairs, which means that if I am using a policy pi and I am in a state S, what is the action value what is the action value for each action that I can possibly take in that particular state. Okay, so it's mathematically we can put this at Q of S and A is going to be Q of S and A, because we are doing this incrementally. So we are going to change the reward based on whatever we have been doing till now, you know, and then we add you know, the GT minus Q of S and A, and we take some kind of a factor here. So my new action value depends upon my current value and all the historical values with some discounting factor. And how do we calculate alpha? The alpha is calculated based on our iterative experiments. Okay, generally the value is the next algorithm that we are going to talk about is called temporal difference method. Okay, so now what happens in temporal difference method is that you know, this technique assumes that the agent is only aware of the states and the possible actions that could be taken. Okay, and the likelihood of each state and the transition probabilities are initially unknown. So those things are not known to the agent. See, the objective is still to estimate the value at state S, but unlike the Monte Carlo method, there is no need to wait till the end of the episode. Okay, so that's the difference. And the advantage of using this method is that, you know, for scenarios where there are very long episodes, or where there are you know, very long set of states and lifespan of that process, temporal difference method can be used. Okay, and if I have to represent this mathematically, then, you know, the VTS can be represented as VTS plus you know, again there is going to be a discounting factor alpha, reward at time t plus 1 plus gamma of Vt plus 1, and a S dash state where it is going to be transition to minus Vt of S. Okay, so it's kind of a complex equation. I don't think GARP is going to test you on how this equation is derived and what this really implies, because our intention is not to become too experts on reinforcement learning, etc., etc. But you need to understand this conceptually, that this combines the immediate reward and the discounted value of the next state. Okay, so this is your immediate reward, and this is your discounted reward of next state. Discounted because there is alpha, and this is a next stage. Okay, so this total reward at time t, or the new reward at time t, is immediate reward plus the discounted reward at the next stage. So this is the temporal difference method. I will not get into more details, and I will like to close this chapter of reinforcement learning here itself. But the intent is to give you an idea of what reinforcement learning is, how is it different from supervised, unsupervised kinds of learnings, and how is this applied in some scenarios, and what is it, what is a reward, how do we find the policy, etc., etc., value method, policy method, etc., etc. We will move to the next chapters now, which are going to be more on how do we measure the quality of some of these algorithms. Then we go on to say NLP, and then a little bit on generative AI. But I'll like to close this chapter here, and if you find this chapter very hard, you can also skip this entirely, because there might be only one or two questions from this chapter. But if you really want to get into the depth of some of these things, it takes time to learn how reinforcement learning exactly works. Thank you.